And on that note, to the space weather. Our planet is not the only body in the solar system to experience extreme weather phenomena. Right now, as you listen to me. On other planets, extraterrestrial vortexes, cyclones with unusual shapes, and extremely violent storms rage, some persisting for centuries. Sometimes these phenomena even occur where you wouldn't expect them, like on the surface of the sun, where, on rare occasions, tornadoes made of plasma form, torn from the surface of the star. They aren't powered by wind dynamics, but by the immense magnetic fields circulating and sometimes swirling in the solar atmosphere. To grasp the sheer scale, the truly gigantic dimensions these tornadoes can reach, here, for comparison, is the size of the Earth. But let's leave our star and its fits of anger aside. Today, we're mainly going to fly over some of the most astonishing weather phenomena that occur within our solar system. And rather than moving away from the sun, we're going to try to gradually increase the level of craziness, starting by visiting the 4 planets where storms are most obvious, the 4 gas giants. When you look at the largest of them, Jupiter, it's almost immediately obvious that the planet's surface is the scene of constant turbulence. As shown in this time-lapse sequence taken by the Voyager 1 probe during its approach in 1979, Jupiter's atmosphere is filled with hundreds of vortices, cyclones, and anticyclones, most of which are of considerable size. To get a sense of their scale, let's briefly place our planet next to the gas giant for comparison. Here, you can see roughly the size of a cyclone on Earth, which typically measures between 500 and 1,000 kilometers in diameter. It usually remains in the atmosphere for about a week at most. Whereas on Jupiter, vortices can be several thousand to tens of thousands of kilometers wide and persist for years, or even centuries. Comparing Earth's cyclones with these vortices quickly hits its limits. On Jupiter, almost 90% of its swirling formations are anticyclones or high-pressure regions. They spend nearly their whole lives in the same corridor, rarely changing latitude. And when they cross paths, they can even merge to form larger systems. Since we've been observing these strange structures on the surface, we've noticed that their lifespan varies depending on their size. Vortices measuring 1,000 to 6,000 kilometers in diameter typically last 1 to 3 years. But the largest ones have existed for so long that we don't know exactly when these storms were born. The Great Red Spot, for example, has been known for certain since at least 1831, when it was clearly depicted in a painting from that time. But it is believed to have probably existed since the 1660s and maybe even earlier, around the edges of this spot. The wind speed is something frightening, because they roar at speeds of around 600 km/h, which is much higher than the maximum speeds recorded in cyclones on Earth. To see this storm continuously evolve in a counterclockwise direction and make a complete revolution around its planet every 4.5 Earth days. One might be tempted to imagine that this structure is just a surface disturbance, but by analyzing the light coming from it in different types of wavelengths, it was realized that the Great Red Spot extends beneath the surface of the atmosphere, and that this vortex goes as deep as about 300 kilometers. Inside Jupiter, although this iconic storm has been raging on Jupiter for centuries, it may not last forever, because it has been shrinking for over a century. When the Voyager 1 probe passed near Jupiter in 1979, its diameter was nearly twice that of our planet. Today, it is only 1.3 times wider. And it is possible that it may eventually disappear in a few decades or centuries unless it regains strength by absorbing other anticyclones. For now, we just don't know. A few thousand kilometers further south of the Great Red Spot, in a different wind corridor, something appeared. In the year 2003, massive vortices quickly merged to form Oval BA, which is now the second largest storm raging on the surface of Jupiter. At the poles of the gas giant, we also find strange rows of gigantic vortices. I'll include the dimensions of a terrestrial cyclone for comparison, so you can see the size of what we're observing. The one at the North Pole is 4,000 kilometers wide and surrounded by 8 similar-sized cyclones, forming an almost perfect octagon. At the South Pole, a cyclone spans 5,800 kilometers in diameter, and around it, arranged in a circle, there are 5 other vortices of similar size. In this sequence, created from images taken in 2016 by the Juno probe in the infrared spectrum, you can see in detail the 6 low-pressure systems that have formed at the South Pole. Each one is as wide as half of our planet. In these images, yellow shows the warmest temperatures at about -13°C, while the darkest areas indicate the coldest at around -83°C. Wind rotation speeds near 350 km/h have been measured, 1,500 kilometers from the center of each polar vortex. Over 7 months of Juno probe observations, everything suggested these polar storm systems are stable. There is no sign they should merge in the future. But that doesn't necessarily mean they've existed for thousands of years near the planet's equatorial band. We've seen stable structures suddenly collapse, vanish, or merge within days, multiple times. After years of apparent stillness, definitely, the surface of Jupiter is like a turbulent and dynamic painting, as if too much water had been spilled on it. In this animation, you can see a time-lapse compiling the surface movements over 24 Jovian days, which is nearly 10 Earth days. When you consider that the gas giant rotates on itself in about 10 hours, you can almost intuitively understand just how fast the cloud layers move here. Unlike the long-lasting vortices, Jupiter is also plagued by stormy tempests that last no more than a few days on the surface, arising within vast regions that are warmer and drier. These storms, which can reach 1,000 kilometers wide, almost always come with greenish lightning, though the reason is still unknown. It seems that the gas giant experiences much more powerful storms than usual every 15 to 17 years. Perhaps even more impressive than the lateral spread of these otherworldly storms is their verticality, because these storms can rise up to 100 km above the planet's average level. It's difficult to realize this due to the vast distances from which these images are captured. But this ocean of swirling hydrogen, helium, and ammonia is filled with huge peaks, chasms, ridges, and valleys. In fact, the Great Red Spot, contrary to most artistic representations we see of it, rises 8 kilometers above the average cloud level of the surrounding regions. To get a visual idea of Jupiter, the best way is still to observe it in the infrared spectrum. Here, the James Webb Telescope shows the deepest regions, the lowest compared to the planet's average level, in dark tones, while the brightest parts are the regions where the clouds rise to very high altitudes. And among these, we find the poles, the Great Red Spot, which appears white at these wavelengths, and the equatorial band, as well as a multitude of small convective storms. The data collected by Juno at the polar vortices, which I showed you earlier, actually allow us to distinguish between the hottest regions deeply buried in Jupiter's atmosphere and the colder ones that rise towards space. In short, Jupiter is absolutely not smooth, and by studying the nature of the light that reaches us from it, teams of scientists have even managed to produce this absolutely fascinating map, which gives us an enhanced view of the elevation of the vortices and other cloud systems above the planet's average level. And with that, we'll leave Jupiter and its features aside to pay a visit to Saturn. At first glance, the atmospheric disturbances of the ringed giant are less immediately noticeable. And yet, beneath the almost uniform milky white surface, there is a complex dynamic and an excess of energy that periodically manifests itself on the surface. Saturn is known to store large amounts of energy and release them once every Saturnian year. One every 30 years on Earth on average. Then, in just a few weeks, a gigantic periodic storm forms, known as the Great White Spot. This kind of swirling, chaotic storm, which usually stays on the surface for nearly 3 Earth years, can extend over more than 300,000 kilometers. Eventually, it would encircle the whole planet. Here, at the top of some very high-altitude clouds, violent winds have been clocked at nearly 1,400 km/h. Saturn also has, at its poles, impressive vortexes with strange geometric shapes. This one has the shape of a hexagon and is about 30,000 kilometers wide, so you could fit our planet inside it more than twice. And inside this hexagon, smaller vortexes are continuously forming, whose vastness is hard to grasp. Just think, this one stretches over about 3,500 kilometers. That's twice as large as the biggest hurricane ever discovered on Earth. Since it was first observed in the 1980s, this hexagon, which spins on itself in just over 10 hours, has continued to fascinate the scientific community. Observing in infrared wavelengths, we revealed an eye at the vortex's center, a stationary storm about 50 times larger than the cyclones on our planet. And swept by winds blowing at more than 500 km/h, it rises about 50 kilometers above the lighter clouds that surround it. Here too, as with the Great Red Spot, it is believed that the swirling winds plunge several hundred kilometers into the planet's atmosphere. And then, not only does it have a mind-blowing geometric shape, the hexagon even changes color over time. In this image, you see it in natural color as it appeared in 2013 and again in 2017. It is believed that the yellowing of this region results from the rise in temperature that comes with the seasonal changes here during the summer. The sun's rays, which increasingly strike these latitudes, contribute to the formation of hydrocarbon clouds, which are responsible for this yellowish appearance. For us on Earth, who are used to seeing clouds winding without any truly symmetrical pattern, these vortices' angular geometric shapes are rather disconcerting. But on this uniform world, receiving 100 times less sunlight than we do, open to the four winds and devoid of any relief, hurricanes follow logics that are beyond our understanding. Powered by the planet's rotation, they feed on currents of hydrogen, helium, and deep supersonic winds, which can give them geometric shapes, all in symmetry. On Earth, researchers from Oxford have actually managed to reproduce many of these strange geometric shapes in a laboratory by using a water and glycerol mix on a slowly rotated table. Another unique feature of Saturn is that it has a storm alley, a region in the southern hemisphere where storms form. Without us knowing exactly why yet, an unusually high number of storms and thunderstorms occur. That's also where the Dragon Storm rages, a recurring electrical storm on Saturn that draws its energy from deep within the planet's atmosphere. Within such phenomena, probes have detected the presence of lightning bolts 10,000 times more powerful than those that occur on Earth. And even though these lightning bolts, which occur beneath the surface inside the clouds, have never been directly observed, we have captured their powerful radio emissions, which have been transcribed into frequencies audible to humans. The giant with rings still holds the record for the solar system's longest observed storm. We actually observed a storm raging there non-stop for almost 8 months. And let's be honest, after seeing so many strange phenomena on the surfaces of Jupiter and Saturn, the gas giants Uranus and Neptune might end up disappointing you. It's not that they're uninteresting, but these planets have been barely visited, and their distance makes observations, even with powerful telescopes, extremely difficult. We only have a few images that tell us they're also very windy. On the first of these planets, Uranus, there are anticyclonic vortices that can be seen in the infrared spectrum and that gain or lose strength depending on seasonal cycles. And if these dark spots may seem small in size, it's because, once again, we lose the sense of scale. Here are our planet's dimensions shown next to Uranus as a reminder. As for Neptune, which is 6 times farther from the Sun than Jupiter, it is swept by the fastest winds in the solar system, in some places. Their speed has been measured at nearly 2,400 km/h, which is almost twice the speed of sound. When the Voyager 2 probe flew by Neptune in 1989, it had a huge dark spot, comparable in width to the size of our planet, with, around its edges and in its wake, layers of white clouds made up of methane crystals. Meanwhile, farther south on the blue giant, a vortex poetically called the Wizard's Eye appeared. 5 years after the probe's flyby, in 1994, when the Hubble Space Telescope turned its lens toward Neptune, the 2 gigantic vortices had disappeared. Because on Neptune, large-scale storms struggle to persist on the surface for more than 2 years. Over the past few decades, only 4 new spots have appeared on the surface, and most of the time, the planet has remained an overall immaculate blue. Oddly, Although Neptune gets just 0.1% of our sunlight, the smaller cloud formations still follow suit, a rhythm closely set by our star's activity. Because Neptune's cloud cover increases and decreases according to a cycle that almost perfectly matches the 11-year cycle of our Sun. Now let's leave the blue giant to visit the surface of the red planet, which is regularly the scene of dust storms. This phenomenon is huge but not unusual. On Earth, in desert regions, sandstorms regularly rise up, thanks to powerful high-altitude winds. Some of the particles it carries can even travel very long distances, sometimes falling back down on the other side of the globe. But on Earth, storms themselves are always geographically limited, while on Mars, they sometimes reach planetary proportions almost every year. The red planet, the scene of dust storms that cover regions as large as our continents. And every 3 Martian years on average, one of these local storms transforms and grows until it reaches colossal dimensions. Here you see the red planet as observed in June 2001 and the same planet a month later, while it was in the grip of a dust storm, a world-class one. Within these storms that envelop the entire planet, wind gusts can reach around 100 km/h, which isn't that high actually. When you consider that the atmospheric pressure on the surface of Mars is about 1/100th of what it is on Earth. So these storms are only able to lift the finest dust, which has a consistency close to talcum powder. Because the Martian atmosphere is so dry, dust can stay suspended for weeks after being lifted, to the point of almost completely depriving the surface of sunlight. This 2016 image from the Opportunity rover shows changing visibility as the storm it's in saturates the atmosphere with dust all the way to the right of the image. At its peak, only 1% of sunlight still reaches the ground. Nearly 10 years later, in 2018, the same rover would find itself at the heart of a storm covering 35 million square kilometers, or a quarter of the entire planet's surface. This time, the amount of sunlight reaching the ground dropped even more sharply, and within a few hours, in broad daylight, it became night. And the sky remained hazy like that for weeks, until the dust finally settled. The event exhausted the rover's last energy reserves, as it relied heavily on its solar panels to recharge. As a result, the storm indirectly killed the robot, which, after 14 years of good and faithful service, stopped there. The surface of the red planet is also the scene of much more anecdotal phenomena, but just as fascinating, called dust devils. These whirlwinds form in the same way as their counterparts that regularly sweep across the surface of our planet. The difference is that on Mars they are much more frequent, and on average 3 times larger. The largest ones that have been observed reach heights of nearly 8 kilometers and could persist in the Martian sky for almost an hour. This one, observed from a satellite orbiting the red planet, is 30 meters wide and rises nearly 800 meters above the ground. Interestingly, some dust devils crossing the rover's path have actually helped them, because with their powerful swirling winds, they blew away some of the dust that had accumulated on their solar panels. The passage of dust devils on the surface of Mars can even be observed, sometimes for several months after they have dissipated. By disturbing settled dust, devils leave traces of their passage. From orbital observation, some of them create formation corridors that are sometimes several dozen kilometers long. Here, devils are born, live, and die as they scour the Martian ground. Okay, I'm about to show you an image with low quality but an incredible subject. Here's what you're seeing. Captured by the Hubble Space Telescope in 1999. This isn't a cyclone, despite appearances, because the formation isn't spinning. It's a kind of polar depression so huge that it could cover half of Europe with its cloud bands, wrapped around an eye nearly 300 kilometers wide. Unlike Earth's powerful polar storms, this formation lacks their strength. It is believed that, exceptionally on Mars, these gigantic clouds form within a few hours when day breaks at high latitudes, before quickly dissipating in the afternoon. In 1999, when Hubble took a second picture after this one, just 6 hours after the first, the cloud had already dissipated. And to wrap up this video about the strange weather phenomena found in our solar system, we're going to take a look at Venus, which in terms of extreme conditions is truly a little slice of paradise. If you like hellish places, well, here, the atmosphere, with its infernal density, is mostly made up of carbon monoxide, so much so that the planet has entered into an uncontrollable greenhouse effect. And at ground level, day or night, at the equator or the pole, temperatures constantly hover around 465 degrees Celsius. It's easier to understand why the Soviet probe Venera 5, which plunged into the Venusian atmosphere in 1969, stopped transmitting. While it was still at an altitude of 18 km for the heavily shielded Venera 13, once it landed on the surface, it managed the feat of holding out. 2 hours and 7 minutes in the harsh, hot atmosphere, just enough time to snap a few pictures. Definitely the bolts. But if, on this planet, neither night nor proximity to the pole can affect the temperatures, altitude can. At the planet's highest point, Mount Scuddy's summit rises 10,700 meters above the average radius. Temperatures can drop to a mere 380 degrees Celsius with a pressure only 44 times higher than what we have at sea level on Earth. That's the best you can get in terms of surface conditions. It's believed that at this altitude a unique snow regularly falls, made of heavy metals like sulfide, iron, and lead crystals. I won't dwell on the madness of Venusian landscapes, I covered that in an episode, but I do need to say a few things. About Venus's astonishing wind dynamics. Unique structures form at both poles, unlike anywhere else on the planet. We've identified the presence of immense double-eyed vortices. It's believed that the origin of these strange storms, which are about the size of Europe, still needs to be investigated. This may be because the atmosphere rotates much faster than the planet itself. Venus's rotation is actually very slow. It takes 243 Earth days to complete one rotation, but its upper atmosphere, moving at about 400 km/h circles in just 4 days. In other words, the Venusian atmosphere rotates faster than the surface does. And it's believed that this impressive difference in speed is what causes the formation of the currents that create the polar vortices. By looking at these images taken in the infrared spectrum, which allow us to see beneath the upper layer of the atmosphere, we become aware of the complexity of the cloud structures that exist, buried deep within. On Venus, storms frequently break out, not near the surface, but in the upper atmosphere. Within these, lightning forms and corrosive sulfuric acid rain falls, which evaporates before even reaching the ground. Because of the extreme temperatures that keep rising as you get closer, just to soften this nightmare vision. Did you know that these storm clouds help make the planet's atmosphere particularly reflective, making Venus the brightest object in the sky, after the sun and the moon, where we will end our journey? And here, I imagine you're saying that since our satellite has no atmosphere, no meteorological phenomena should occur there. And yet, flashes are regularly observed there, and have been for centuries. These sudden appearances of bright jets on the surface of the moon are called transient lunar phenomena. The earliest one mentioned in stories dates to 1178. The video you are about to see was made by an amateur astronomer who was lucky enough to capture one of these flashes. Flashes that mostly aren't flashes at all, because these flashes are actually almost always caused by impacts from tiny meteorites that hit the surface of the moon, producing a burst of light that is as sudden as it is short-lived. Today, when an event like this is reported, it's even possible to find traces of the small impact crater recently formed after the appearance of certain flashes in images of the moon's surface. It still remains mysterious, and to explain them, we are trying to choose between different hypotheses, involving outgassing near craters or electrostatic discharges caused by lunar dust. I hope that the next time you take your umbrella to go out covered, you'll think about Jupiter's storms, Saturn's hexagons, and lunar flashes. And, just to bring you back down to Earth, I'll leave you with a mini tornado captured at the abyssal plain. 4,000 meters deep in the oceans of our planet, to explore the surface of the sun. As you may have never seen it before, it's over there. And to dive into the hell of Venus, it's right here. I'll see you very soon.